talked about material extrusion, which is polymer based technology. So I thought instead of covering all the polymer based technologies, I think let's start covering metal based parallelly, so that you will also get some idea which how the process in terms of metal and then parallelly polymer based. So morning we have actually talked about desktop popular 3D printer, which is a material extrusion. So another when it comes to the other three more process, we will try to cover in the later class. I think we'll also try to cover in this class itself the binder jetting technology. So when it comes to the powder bed fusion, how many of you are actually aware of powder bed fusion? Let me see. None? Okay, so that will help me in terms of going through the depth. So this is actually the very popular, when it comes to the metal-based additive manufacturing. So as I said in the morning, mainly there are four, classified in terms of based on the process of the way that actually they use power source, or the way that how the material being fused. So when it comes to the binder jetting and then powder bed fusion, so there is a similarity when it comes to the technology, right? So what are the similarity? I will let you know in the following slides. So I think we have briefly talked about sheet lamination and then directed in deposition. So when it comes to the metal-based additive manufacturing, this is the first one in terms of when it comes to the technology. They also called SLS, selective laser sintering. So when it comes to the selective lasers, powder bed fusion technologies, so there are different names that you will actually find in the market, which is direct metal laser sintering or electron beam melting, and then you will find selective heat sintering, and then selective laser melting, and then selective laser sintering. So I think we have actually talked about selective laser sintering, which is SLS. So this was the first the name that invented when they started the technology, which is the metal additive manufacturing. So so that's where I think the powder bed fusion technology started. So if you see that why they call the powder bed fusion, right? How the term came, etc. We'll go through the later part. So briefly, if you see that whenever we actually talk about the metal, right? Whenever we actually talk about anything that you want to actually convert or process any metal, you need to have mechanism to fuse the material, right? To melt the material. Then only you can actually form the shape. So there are different ways in which you can actually fuse the material. Like example, if I actually talk about the casting, right? So initially maybe the material may be in the raw form, a raw material, or maybe it is in the form of a solid structure, and then you actually melt it, and then you actually form the shape when you actually pour into the different dies, right? Similarly, you might have actually seen the powder metallurgy concept, where you might have actually prepare the green part, right, where you actually put inside the molds, and then you actually use different binders, and then try to prepare the shape of the powder components, right? And then you might actually use a different binders to stick the powder together. But and then that is not the final shape, the final component, because you just formed the shape, right? So if you want to get the metal component, so you need to actually go for a heat treatment heater, right, which is basically actually put inside a furnace, right? So then actually you get the metal component, right? So which means, so that is a conventional, that when it comes to the forming a shape, right? One being a casting, other being a powder metallurgy, and then there are other processes where you actually need to have one or other mechanism to fuse or melt the powders, right? So when it comes to the the technologies like additive, where especially powder bed fusion uses either the laser source or electron beam as a source for a fusing a metal or a fusing a powder, right? So and then when you actually fuse them, and then you actually put them under atmosphere, like under the vacuum, especially when it comes to the electron beam. So as all of you know that electron beams are very sensitive, so they only actually work when you have create a vacuum. The reason being, if you actually work in open environment, it will beam will actually diverge, right? So I will come back to the technology later part. So what we try to do here is we try to create a the component or create a layer by using either the laser or electron beam. So we use this one of the sources as a for a fusing the material or fusing the powder, right? So all the if you see across the powder bed, the fusion, the bed is means you have actually the bed concept. Why? Because we have the reservoir, and then we have the spreading unit, and then you have the basically where the reservoir actually shifts as the material is being actually spread. So all the LPBFs actually involves a very similar concept, which is in every machine that you will actually will find spreading the powder, right? You actually spread the powder. So that is a very basic concept in all the LPBF techniques, right? Once you actually spread the powder, now based on the CAD information or based on the where material you are supposed to fuse, you will only will selectively will fuse in that area only. And then there is the material that you have not actually fused, the material that you have not actually passed your laser, right? So that powder material actually will stay there itself. So that material will actually will stay next to your fused material, which means there are three different zones in this case. One is the fully fused metal or partially fused metal, and then not at all melted, which means wherever the laser is actually fully coming in contact, you will actually you'll see that fused material, and wherever that is slightly in contact with the fused, but it is little bit away from the unsintered or fused material, will actually have a under like partially sintered, and then the rest basically will not at all, laser will not at all actually will come in contact. So all the all the powder bed fusion technologies, there, as I said, there may be n number of names, DMLS and then EBM, or including SHS and then SLM. So they all actually work in a similar inline that simply spread the powder, and then you actually selectively melt the region, right? So but there are cases like, again, so since if you actually establish or you actually start a one technology, and then you may be having different way to spread the powder, right? A different way to fuse the this thing. But again, all the technologies are actually work on of spreading. But again, you may have the once, say example, in some machines you may have the different rollers to spread the powder, right? In some cases you may have the blade to spread the powder, but you are, at the end of the day, you are actually spreading the powder, right? So then what happens in some cases, you will have the hopper, like where you actually put the powder, and then you actually try to pass the through the hoppers. Or here, when it comes to hopper, you have more in terms of control. Like example, you want to change the material, you want to actually play with the different materials. So there you can have more advantage for going for multi materials or so on. But whereas in the case of a reservoir, so what happens? You have the reservoirs, and then reservoir is actually moving up and down. So I will take you show in the next slide, where you actually supply the powder every time or every layer as you actually build the layer, right? So almost all the LPBFs actually will fall in this category. So if I see if I show you this image, yeah. So there are again different the technologies that I actually talked about, like example, selective laser sintering, and then selective laser melting. So the difference between the sintering and the melting, mainly if you see that the way that you actually fuse the material, so the way that you actually supply the temperature to the melt pool, right? In one case, you only just allow to form the, or you are just only sinter it, so you are not actually fully melting it, right? So that is where you actually make a component where you just fuse it, right? You actually control your heat source such that you don't actually fully melt the component or fully undergo the material phase transformation, right? So you just, like example, imagine neck formation in I think some of you already heard of powder metallurgy. So you might have actually heard neck formation, all that, etc. So there you just allow only to form the neck formation, but you don't allow to just to fully change the face of the sintered component, right? So but whereas in the case of a selective laser melting, so you actually go beyond your melting, so that it actually changes the face of the powder particle, which means it may not actually stay with the powder like in center form. So here you may have to actually go for another layer, so another post technique, which is actually you need to go for a heat treatment for you to prepare fully densed component, because in this case your part may not be dense 100%, but in this case your part may be fully densed, because you actually allow or you give more heat, right? So that it will actually changes the face of the powder particle, right? So again, similarly, one advantage about this powder bed fusion technologies. So if say example you have a complex part, or say example you want to actually print some overhanging surfaces, or you want to have a support structure that is actually required, right? So in this case, as I mentioned, wherever the material that is actually fused will actually will form the shape, and then there is a material that which is actually partially sintered, or material which not at all actually sintered will stay there on the bed itself. So that material actually will act as a support structure, right? So that is the beauty of this technology, because whatever the material that you have not actually sintered, so will act as a support structure, which may not be the case in other technologies. Like example, if I talk about DED or other technologies, you may not have that support where your powder, because powder is in the form of a solid powder, so that will actually always will help us building any layer on the top, right? So there may be some penetration, there may be some level of material, the lower side of the material actually will fuse it, but and then we actually can build material on the top, right? Which in way it will help us making a controlled or that layer, right? So what you have to do is when you actually have such a support structure, technically you can build any complex shape. You talk about, if you design it, so you will be able to actually fabricate. Such is the beauty of this technology, which if you compare any other technology, it is not that straightforward when it comes to printing of a complex shapes. That's why this technology is very popular when it comes to making of a complex shapes or implants or precision parts, right, or so on. So I think some of the parts that you have actually printed. So and I think after this they will actually will take you the lab where you can actually go through it. There are some parts also in my vehicle. I'll show you the later part. So where you actually and if you actually have the controlled environment where you can actually even make better in terms of part without any impurities or so on. So this will help us in terms of making the process or complex shapes. So as I said, you may have the process may use either the roller or blades to spread the powder. So example, if I show you the uh, you know yeah, these are some more other processes. Example, if I talk about selective heat sintering, here similar to the selective laser melting, but selective laser sintering. But what happens here? Instead of you actually use a laser, right? You use actually head. Say imagine this is the head, right? And this is actually the basically the exposed that area to the melt pool or the powder. So entire area will be actually exposed to the melt that powder, which means at a layer, one layer itself can be printed at a given point of time. But and then this good, I mean, good thing about this technology is you don't need to actually use any lasers, right? But you can actually take advantage of the heat basically head, because the your head is what actually heated. So by using a heated head, and then you can actually sinter it. You will not be able to melt it, but you can actually sinter it, right? And then you actually form a one layer at a time instead of a point by point. That is actually most of the LPBF actually works on a point by point or line by line, right? But this guy actually works on an area. You can actually entire area. This is example. Imagine here you actually have spreaded the powder, right? Imagine this is your head. So as soon as head goes there, that entire area can be centered. But the size of the head, the profile of the head is actually important, right? So this is actually will help entire area at a time. But again, this is not actually the laser, but because you cannot actually change the head, and then you cannot actually change every time the patterns. So this technology did not take forward, and it is not successful in terms of making a metal component, because it is not easy to change every time or process the technologies. So again, DM LS is another which is the same whatever the SLM. It's basically all this, since the technology was so good. So every alternative or other industry want to actually enter into this field for making this metal 3D printer. So as I said, in the previous class also. So if you actually have the trademark for the names, other company cannot actually have the similar names, right? So that's why you'll find a lot of the although technology is same, but you'll find different name, because the original the patents actually got expired. And then later on, people have actually started using the electron beam for making or fusing of a material. So again, this will only work under vacuum condition, because otherwise the beam will actually will divert from the focused this thing. And this is one of the bigger, if you see that, and especially if you want to actually make a high temperature metal, or if you want to actually prepare a high temperature material, and then there actually they use this kind of the technologies, right? So and then again, so all this if you see, right, so whatever the five are different the process that I actually talked about in the previous slide, they actually simply follow the same concept of example. This is the reservoir. These are the basically This is the powder. Initially, this powder may be somewhere here. This entire the reservoir will have the powder, right? And then this is actually the bed. Initially, will be here somewhere, right? So what happens? This roller will take some powder, right? And then you will actually will push to this side, which means you will spread onto the bed, right? Say example, you'll spread about like 0.5 or 1 layer, right? And then you have the laser. The laser actually will come and say example, imagine this is the bed initially will be here, right? And then laser only will come and then will fuse material in this portion only, right? Similarly here, laser only will come and then fuse. That's why this is called selective laser sintering. Although if I see from the top, so I'll have a area of say 100 by 100. But if I see that amount of the area that I will be picking maybe less than 10%, only in that region I will go and then I will melt it. So that's why in this region, so this is only the reason where this is a selected area, although the powder is actually spreaded on the bed, entire bed, which is 100 by 100, but I will only selectively melt in this region and this region. But and then once that selectively melted, this bed actually will go one step down, which is the layer thickness. Say example, in this case, say 0.2 is the layer thickness. So I will lower down by 0.2, which is means initially that small layer is actually formed, and then that much of the bed is actually will come down. Similarly, this guy will rise. He will rise by another 1 2 so that the powder will be actually spreaded on the already deposited area on the top of deposited. At the same time, there may be also other areas that were not at all melted, because when you actually spread it, so you only selected some region and then you have melted, but other region you have partially sintered, or some region you have not at all actually melted. So there also again you have to spread, which means now the powder is actually being spread on the already deposited layer, on the top of the deposited layer, at the same time also spreading on the powder is already spreaded. When you actually do the next time, you are also trying to compact, right? Otherwise powder will actually vanish or will try to fly, right? You need to actually create enough compact where you actually create the bed, right? That's why called the bed. That's why they call it a powder bed. You are actually creating the bed before you actually fuse the material. Once you create the bed and then you actually fuse it, now like this you actually go for another layer. Say example here, another here, right? So if and then you similarly raise your the reservoir, powder reservoir, and then you again spread it, and then again your laser will come, and then now this time this area will be fused, where it will be coming, and then again it will be fusing. So similarly, until you actually get the final component, you actually follow the same technique. But what is the most important in this case, right? So if you see this entire region inside, this is not at all actually sintered at all, right? But you will be able to actually print this. If you see that conventional, right, it is not possible. You need to actually have a separate strategy for printing this in a conventional. Because say example, if I talk about a material extrusion or other technologies like DED, so I need to actually provide support structure, which means I need to actually parallelly think how to build a support structures, how to build the bridges, how to build what material I should use and how much density I should maintain for building of a support structure before you actually build a actual or model material. We call model material means actual component, right? So in this region, I did not even bothered, right? Looking after the support structure, because all the support structure, all the material, that powder material that is actually available, where it was spreaded and then partially some maybe wherever the powder is actually coming in contact, that area may be partially sintered. But and then there is a large portion of the powder which is not at all melted, but now it has actually created a bed for the model material without even working on what kind of a support structure that I should use it. So you will be able to actually put enough support structure. That's why when it comes to the powder bed fusion, so you no need to actually worry about what kind of a support structure you should put, because there is already the powder is already available for us to build the model material. But and then there are cases like where we need to actually worry about how much the support that the model material and then support structure that we need to maintain, right? And also sometime, say example in this case, right, it is a straightforward, but we can actually print and then on the top. But there are cases like where you have the different parts, so there we need to actually use a different the strategies for printing of such a component. So all these processes actually follow the simple procedure. I think I've already explained. I think a lot of others also explained about like taking the three-dimensional part and then process it, and then you actually get into slicing and then convert that into G code, where you actually you understand what how machine can understand, right? All these things actually after you all done it, and then you need to make sure the powder is actually in place, and then make sure you have enough the powder is available, I mean sufficient, so that you don't need to actually stop in the middle of the printing and then you actually change the the powder, right? Because example, if you actually only put the small powder, right, and then you only printed halfway, right, and then again you have to actually come back and then redo it. So to avoid, you need to actually provide enough or put enough the powder such a that so you don't need to actually worry about adding the powder every time, right? So a lot of this printers will have the and it will consume lot of powders. Usually it is recommended that you actually put sufficient powder, so that, but one good thing is, so you don't need to actually print one single component. You can as well print multiple parts or multiple at the same bed, because the time will be almost same in terms of if you talk about the components and the number of smaller component. But and then now there is always challenge, right, when it comes to the technology, because yes, it is good, it is actually printing, right, but how about it will take a lot of time, it will take some time, hours, sometime it will take 10 hours or 20 hours or 30 hours, because in this case disadvantage with respect to the technology is, so you are actually using the line by line, which means you will be actually, say example, if this is the bed, right, so you have to go like this only, line by line. Laser has to actually go line by line, and then only it will fuse entire area, and which means it will take lot of time, right? Instead of that, can we actually use a multiple lasers? Can we speed up the process? I think that's where actually the technology is actually taking now. Now what they're doing is, so they're actually using a different mechanism or different optics, where you will have multiple sources, right, and then you actually selectively select the region, which region that you want to actually, say example, if it is 100 by 100, and then one portion, like 1/3 of the portion will be taken care by one laser, other 1/3 will be taken care by other laser, and all together come and then you start actually fusing it. All that means you are actually increasing the speed of or the printing speed, so that you take less time for for a printing. So in fact some companies have actually tested using more than 8 lasers, and then I think many are actually trying, because one when it comes to the technology is the speed, especially the powder bed or anything that we actually talk about a powder based, because the powder is small, it is like less than 80 micron or 120 micron, right? So if you want to actually print a, say, 500 by 500 component, think about how much time you need for printing such a large component, right? So to come out of that challenge, so people or the industries have actually started using different the lasers, and then started faster in terms of printing speed, right? So again, there are again challenges when it comes to the technology, right? So the powder handling is one of the challenge that I think when it comes to the technology, right? So here, when you, as I said, when you actually put the powder, right, you need to have sufficient in terms of volume of the powder. So then only you can actually avoid any changes. Otherwise, you have to come from beginning, right? You have to actually again start from beginning, and then you have to put the powder again and again, right? So to avoid that, it's always better to have enough the powder is available, so that you can actually uh, no need to worry about the, yeah. So this is how typical the powder feeder or hopper. So when I say this, like here, some of the companies actually started adding a multi-material also. Since this is not a reservoir, like where it is actually coming from the bottom, where you cannot actually have much in terms of flexibility in terms of varying. But here you can always actually have the hopper, right, where you actually change the powder, right? You can actually have the different composition. You can actually supply the powder externally, and as and when you want to actually change every layer different material, right? But and then changing alone will not be sufficient. You need to also make sure, so you need to have that those laser parameters, so that it can be melted or uniformly fused with respect to multi material, right? So sometimes people actually use a different the blades, or and sometimes you have rollers, right? So that when you actually use the roller or blade, so it will actually will help us creating the bed. It will help us creating nicely the bed for, so that you can actually melt it. And also, as I said, if you don't actually have this roller or the blade, so the each and every layer you cannot actually control the powder. So it will simply will start flying, especially when you are actually using a different argon and then helium gas. So they always try to carry out some of the powder. To avoid that, you need to have that compact enough so that the powder will not actually will fly. So these are the the challenges. And then again, another interesting or a good thing about the technology, and also a little bit of when it comes to the limitation point of view. So powder recycling is one of the major issue when it comes to the technology. The reason is basically when we actually put the lot of powders, like example, if I talk about the machine that we have, we need at least say 20 kilos for to just to start. Maybe Prachi can correct me. So just to start, we need that much of material. But one good thing is we can always make sure that all the powder can be, even if you have not used the powder, right, it can be actually recycled, which means the 20 kilo the powder that you actually bought can be actually converted into parts. You may have different time frame, but there is no waste of a material, which means whatever the material that you have actually bought, it can be actually converted into the fully the part. But then again, is it okay if you can actually reuse it again and again? Because there are some powder which is actually in coming contact with the fused parts, which means partially sintered, right? How much how much it is acceptable in terms of partially sintered powder, right? So I think there are few the formula they use. Example, 1/3 of the reused material, and then the remaining is basically 2/3 will be a fresh material. So we can always have that combination, so that you will not actually compromise on the parts that you actually print. So one good thing is you'll save the material over the time, but to start you need to actually have the more material. So that is a disadvantage about the technology. But again, a lot of developments are actually happening when it comes to the the technologies. So as I said, so you can change the material compositions, and then you can go for adding the materials like as I said, one of the best ways you use a different hopper, so that you can actually control the powders, and then you can example, as I mentioned, you can have a one third of mixtures like you unused powder, and then one third of overflow, and then one third build platform powders, so that you can actually balance it, and you will not actually waste that much of the powder. Maybe let's see this video. So this is the initial say example. You want to have multiple parts to be printed, right? So you can see how nicely you will arrange it. So now we need to arrange exactly where these guys will be placed. So this is almost like 300 by 300. So now we actually started printing. This is one layer is done here. This is one layer, and then since this has only one laser, so but imagine if we have multiple lasers, right? One laser can be printing this part and then like that. So this is what I was talking about it. So you see that how nicely the blade is carrying it. So this is the laser. So if you see from the top view, okay, so once it is done, right, then the next step is now you have actually put the lot of powders. Now beneath of this, I think you have all the components printed, right? Sometime you may have you may need a some parts which is larger, or some part maybe smaller, but you still cannot take out in the middle of the print, right? You have to wait till the final part which is having the highest in terms of the height, and then you will actually take out after all the components. And then you need to actually take the powder initially, because I think you have to use a vacuum machine to take out all the powder. Of course, as I said, you can actually recycle it, but I think first thing is you have to take out all the powder. This is what is actually trying to do it. So now you can see that. So now you can see that some of the components, although he has taken the powder out, but you still can see some powder is here. You still can see some material is here. So while generating, so you might have actually observed there may be some partial powder is actually melted. Partial material is actually sintered. Whichever the material is actually sintered will stay with the part, which is like partially sintered. But then that's how it will help us printing actual material, especially before you actually print the actual, especially when you actually print the top surface. There you need to have at least 1 or 2 layers will be actually melted, or if not fully melted, the partially melted area you will find it, right? So that's how you will actually find it. Sometime for creating a better structure, so deliberately, so they actually give you some powers to the the support structure, so that you can actually build a better support also, right? So that deliberately that they have actually made such a that you can actually get a better in terms of the support for a model material. You can see that how complex the shapes here. You think about, like, if you want to actually make this many components using a traditional manufacturing process, how much difficult or how much time it will take for just processing each and every file, or machining of these components. So now he's actually taking to the furnace, so that if there are any partially sintered, so that will be like a fully melted, right? And if any impurities, that can be actually eliminated. You can see how complex shapes that you are able to actually manufacture using this technology. Yeah, so there are even different variants. As I said, based on the laser power, right? You will decide whether you are actually going for sintering or melting. More the temperature, that will go for which is melting, above the melting point of a given material. So we'll go for a melting. But if you are actually doing something like below, which is like basically nothing but a sintering, right? So you can actually select the laser based on the temperature, which is low temperature processing, which is sintering method. And then you can actually select based on the metals, and then you can select the based on the polymers or ceramic material, right? And then you have again line wise or layer wise, right? So being I think as I said, layer wise, it will actually be speed, it will be more when it comes to the line wise, because you're processing line by line, right? And then you have the different beams, like sometime you may have a electron beam, or you have a laser beam. So these are the some of the variant. So you will find one or other system actually will fall in this the category, if you see any system in powder bed fusion, right? So the lower, that basically, especially I talked about low temperature the processing. So these are actually designed especially for polymers, right? For not for the metal, but where, because you need a lesser temperature, lower temperature, so that you can actually fuse, and especially you want to have a small the components or ceramic or low temperature materials, there actually the uses. So and then you have the ceramic based, again I will not go through the individual the techniques that we have. There are a lot of advancement in terms of this technique. Again, when I talk about line wise and then layer wise, so one I think disadvantage about most of the these printers, because we are actually using a line wise, right? So but if we know, if we can actually convert that into more of area wise, so that's where the speed actually will pick up. Like example, we talked about SLA, and then we talked about DLP now, right? So how many of you actually aware of DLP, direct laser, what is it, digital light processing, right? So it is basically projection method, right? Which means when you actually project it, entire area will be, projected, entire area will be actually, fused or, solidified. But here, instead of entire area, we are actually going by line. But I think one technology actually, as I said, they actually did on an area wise, but still they have not actually succeeded in terms of making the part which is very complex shapes, and then I think somehow they could not actually do it. But what I think they are trying to do now, so they are trying to come up with the multiple lasers, multiple beams, electron beams, and multiple lasers, so that it can be actually divided, your part can be divided into multiple sections. Then you can actually use all the lasers, or sometimes you may have multiple components to be printed, and then each component will be printed, or that layer can be printed by the respective laser, so that you can actually increase the speed of the whole process. So a lot of innovations are actually happening in that direction, right? So I think we have talked about it, some of the areas, I mean the namings. Yeah, I think I have already explained what are the steps that are, these are very common when it comes to the any other additive manufacturing, where you actually prepare the CAD file, and then after you prepare the CAD file, now you go to the powder or system that you actually keep enough reservoir, enough powder in the reservoir, so that you don't need to actually change in the middle of the printing. So this is just the process wherein you can actually, I think I have already explained. I think one of the interesting when it comes to the process, right? So if you see that when we actually see the technology, so this is what the reservoir where the powder is actually coming to this side, and this is where you are actually generating a melt pool, right? So if you see this is actually the melt pool, right? So now you can actually see what are the problems in this. You can see what are the expertise that you need to understand this melt pool. The process was easy when we actually started. When we saw the video, we felt wow. But if you go into the physics of the process, you can see we need a mathematician, right? You need to have a mathematics background. You also need to have physics background. You need to have the materials background, right? You also need to have the mechanical background. So this is actually the interdisciplinary problems when it comes to the melt pool. Because when we talk about the materials, right, we can actually see how fast the melt pool is actually cooling, right? How fast it is actually solidifying the printed structure, right? How fast it is actually cooling is actually happening. But and then we can also see that, like example, if I want understand mathematically how if I want to actually simulate, I need to actually have that what kind of a heat source, right? What is basically model that are actually used. You need to actually have that better understanding in terms of mathematically, and then what kind of flow, and then lot of fluid mechanics, right? The power, the fluid is actually, you can see a lot of material is actually flowing, right? So you need to have that again understanding about like how the laser, when a laser actually interacts with the powder, so what is actually happening, right? A lot of physics is actually involved when it comes to the process. Though that's why this is not a like simple just one mechanical problem alone. So this has a material science, and then a physics and mathematics, and then mechanical, all put together. You need to have a better understanding when it comes to the printing of a quality of a component, right? What will happen if you actually change the material? What will happen if you actually change the patterns and the strategies? How this behavior will actually happen? And also when you actually interact, when laser actually interact with the powder, and what will happen to the layers which are actually below, right? And what will happen if there is actually any powder below which is not at all melted, right? And if there is any melt pool area below, right, or if there may be partially heated bed, right, how it actually behaves, right? So lot of interesting work. It is not just one manufacturing alone can solve such kind of a problems, cannot even solve alone by a mechanical. Forget about like if I talk about like physics, and you can see that all the interdisciplinary background is actually need for solving, especially as I said. So to understand material science point of view, right, how the powder is actually interacting with the laser, and then how when you actually, and what will happen if laser moves in a different direction, and then and what will happen if you actually, what is happening when you actually go for higher melting, some of the powders actually flying, and then how much you are able to convert the powder to the the part, right? So many interesting problems that you can actually see, right? Example, if I talk about this simple, yeah, so this is another video. Then you will, here you will find two different lasers, and then you see how when you actually have the two different lasers, and how two lasers actually will help speeding up the process. So you can see here multiple lasers. So one laser is actually doing one of this area, and then you can see L is with one laser, S is another laser, where you can actually speed up the process now, right? See now, once this is done, and then you have another layer is actually, the bed is actually spreading the powder. So you see, still a lot of powders, but this is only the melted area. Okay, so uh, I will just get some more the issues that you will actually will find. So this work we did when I was in Stanford, which is Stanford Linear Accelerator Laboratory. So what we did, I think here is, so if you see that typically what happens, so you have the laser is coming, and then when you actually pass around it, right, when you, especially when you have the corner, right, so when you try to spend like you are simply going like this, right, but at the corner you will be actually spending some amount of a fraction of second extra, right? So that small extra time, how much it will create a problem, you will see. Not sure if I have the video. So these are the some of the melt pool dynamics that we can see. A lot of voids formations. When you actually cut the sample, that you will actually will find some of the voids. But how we actually eliminated over the time, we'll see that. So you can see that when you actually change the track, so this is that the track that is actually coming. So you have the point. Yeah. So this is actually the track that it is actually supposed to pass through it. So especially when it comes to the turning. So since this is where you actually change your the stepper motor, right, to that other motor, where it actually you may require to spend small extra time, right, and then you actually change the track, and then during which you will actually find this is how the turn point, and then you will find because of you have spent some time, so it will actually will generate a depression, and then it will form the voids underneath of the layers, right? And then this is the, and then after it passes through it, and then you will find these voids because it creates a depression. I don't know whether we have the video of this. Yeah, so you can see here. So this is what the actual constant power. When you go for constant power, so when you actually turn it, and then when you observe this, so it will form and then it will create the voids here. But in this case, we actually mitigate it, and then you will never find it. Yeah, you see this? This is actually the voids formation happen as soon as it takes the turn. Now here you will find nothing in this case, but here you will actually find what we did is we again further mitigated all the how much time that you are actually supposed to spend, how to control your laser as you come to the corner, because there are ways in which you can actually control your heat. One is basically you either control you switch off your laser, that is a one way, or you actually reduce your power, right? So if you actually switch off the laser, and then you will have a lot of material will not be fusing, even the fraction of second. But you can actually mitigate in a controlled intensity of the lasers, so you will be able to actually achieve without any porosities, right? So example, we did also some simulations. So you can see here. So when you actually when you take the turn here, and then you will find some depression here. Yeah, this is where the depression, right? So this is how the void formation actually happens. So that's why you need to have better control when it comes to the turnaround, right? So you need to have a better understanding about like how how it behaves when it comes to turnaround. So this is the simulation work, and then that is the experimental work that you will actually find. Again, we'll see one more time. So you can see that how the temperature is also actually distributing. So since you have the temperature here also, which means this area is like a more of easy to penetrate, easy to actually create a depression, because you have actually created enough thermal or the enough in terms of temperature here. So where your melt area will be like a more of a dynamic, right? So that is just to give you that idea of one case study that yeah. So and then you, as I said, there are simple example that I told you, so selective sintering and then melting, where just the matter of how you actually fuse the material, how you can actually control your temperature, and of course based on the materials that you actually use it, so we can actually use the temperature, what kind of, whether you want to go for sintering or melting. So then you can actually decide what kind of the technologies. I think these are some of the applications that we actually talked about, how this technology will be used for a different so other applications. So I think, yeah, these are some of the examples that you will find it. Last one video. So this is a case study of conformal cooling channel that you will see that how nicely that they will print. Think about if we want to actually print this kind of component in a traditional machining or casting, you will have a lot of challenges when it comes to making up this complicated the shapes. So yeah, this is a little bit of manual method that they are removing the powder. You can see this how nicely they have printed. Yeah. So again, there are a lot of advantages when it comes to the technology. Of course, nowadays material availability is easy compared to few years back. So it is easy to get the materials or so on. I think that's about the technology. Yeah, so I think selective heat sintering is, as I said, this is nothing but when you want to actually print entire layer, so we can actually use the head and then you actually focus it. But again, this technology did not take much in terms of the commercial this thing. But I think just to give you examples.
This is the blueprinter.
This is no more in the market. This is a much old in terms of technology.
This is how it looks on the inside. In the center, there's the building chamber. This is where the models are being printed. There's a display showing the status of the printer. And as you see, there's no buttons on the printer. That's because it's all controlled from a browser. And if you follow me, I'll show you how it works. You type blueprinter.local. And you'll be taken to the user interface of the printer. This is a graphical representation of the build chamber. And it's in here you control everything. We can drag in our STL models. I'm dragging a lamp design from a designer called Dissinghoff. Once you're satisfied with the layout, you simply push print,
and the
printer will start printing your model. We are distributing thin layers of plastic powder and sintering the cross-section of the model to the structure. You layers your model. Printing is now done. Play now tells you to empty the chamber, the models. When it's done, you take the
so this is
cleaning station. So what we do is placing the build in the cleaning station.
So they have actually took entire the chamber where the powder everything. So it is easy to manage. But again, you need to have better in terms of removing the powder.
Depending on the build size or the geometry, it can take anywhere from 5 minutes to 30 minutes. After you have waited for the printer and the finished model. This is now the finished Dissinghoff lamp model. It's a good idea to rinse it in water, but except from that, it's a finished model. With an actually bulb in it. See if you're happy with the design, and if not, other examples. Quite flexible part. This is a simple mid. Take straight flexibility of the part.
Yeah, so this is another technology. Again, as I said, this is not there in the market, but just to give you that some of the powder bed fusion were also used for polymer printings. So yeah, that's about the powder in terms of a laser, but we also have the electron beam. So I think the the concept when it comes to the powder spreading, and then all the process in terms of taking CAD file and then slicing, everything is same. Just you'll be only changing the power source, which is like whatever the earlier you are using for laser. So here you will be actually using electron beam. But another advantage about this technology, you can actually prepare very high temperature materials, which is like not possible when it comes to that lower temperature lasers or mid variants, because you can actually achieve high temperature when it comes to electron beam welds. Or you might have actually seen a lot of the high temperature materials uses for they uses for electron beam, even both melting and then as well as welding, right? So this is actually the configuration that you will actually will find. Again, they also have the hoppers, the side, and then where the beam is actually coming. So one tricky part about this technology, without vacuum, you will not be able to actually pass the beam, because beam will actually will interact with air particles or oxygen. It will divert away from the melt pool, because of which you have to have fully vacuum condition. So then only you will be able to. In fact, some of the tests were done, and then it was even successful when it comes to the printing of in the space as well. So they have done it using a DED technology. But again, uh, that is another topic that I will come in the later part. Here you can actually see the beam is actually used for making the components. So now I think GE is actually acquired. Earlier they started Arcam. So now I think the company is actually acquired by the GE Additive. I think as of today, I think they are the one who makes all the electron beam powder bed fusion. Of course, recently there are a few other companies also started making electron beam variants. But again, this actually requires a lot of maintenance. It's one good thing is you can actually make a complex or high temperature temperature. Example, as I talk about, you have the filament heated anywhere 2500 degrees Celsius, which is not possible when it comes to typical laser, where they talk about like 1200 or 1000 degrees Celsius, right? I think I have the video.
Additive manufacturing
So
offers
this is
greater
electron
freedom
beam
in
based.
design and allows for the creation of optimized parts that are not constrained by the limits of traditional manufacturing. Arcam EBM has the unique ability to tightly stack parts within the build in order to increase productivity. An optimized build file is sliced and loaded into the Arcam EBM system. Following this, metal powder is loaded into the machine. The build chamber is then closed and a vacuum is created to ensure a clean, controlled environment that allows for the processing of reactive material. Next, Arcam EBM's powder layering system evenly distributes a thin layer of powder on the build area. A powerful 6 kilowatt electron beam heats the powder bed to the optimal ambient temperature and then proceeds to melt the powder. First, contour melting and then patch melting. The electron beam unit generating the beam contains no moving parts, allowing for extremely fast and accurate beam control. The build environment is kept hot, reaching temperatures exceeding 1000 degrees Celsius, resulting in no residual stresses and allowing for the processing of crack-prone materials. As each layer is completed, the build is lowered and a fresh layer of build powder is rigged over it. This process repeats, growing the build one layer at a time. When the build is complete, the tank is extracted and the Arcam EBM machine is prepared for the next build.
Yeah, so that's about the Arcam. Yeah, so these are the some of the the steps that I will not go. I mean, as I said, you can actually print nicely, almost high temperature the materials. you can see some of the components that they have actually printed. Yeah, of course, every technology will have some limitation. I think so. Since I thought I will cover another technology, I think we'll stop here. Any questions? Yeah.
Sir, will the particle size vary depending on the material that we choose? Say, for example, we want to melt equivalent
Hmm.
and titanium.
Hmm.
Will the particle size vary for the maybe SLS or SLS?
Particle size, you mean to say
Powder size.
powder size? Depends. Like example, see, if you are actually giving the same powder size, right? So, but if your melting temperature of these materials may be different, right? In that case, you have to see how, how, what is the behavior of that powder when you actually interact with this much of a power, right? Your weld pool may be better, may not be better. If it is a better, means it has a better compactability between these two materials, right? If there is no the proper weld or proper the pool, right, which means they are not actually compactable. Like example, if I talk about the extremes, titanium versus aluminum. If I actually give the same heat of powder, say example 80 micron of titanium and then 80 microns of aluminum, aluminum just it will evaporates, but titanium may print only partially, or partially it will be like sintered. If I actually give the power in the middle of the, like where it try it, if I say example, if I divide it and then give you something like intermediate power between the melting point of titanium, melting point of aluminum, it will not work, it will not go well, right? That's why you need to see that melting point of these materials are very important when you actually deal, or when you actually go for when you actually mix this material. That's why the best way is you actually make vary that composition such a way that have a more in terms of materials, like example 90% of a material A and 10% of material B, and then you know that whether they're okay or not, right? It is also possible that up to 30% your there may be good compactability, right? At least you can actually mix up to 30% of material B. You start with the 5% and then you keep on increasing, and then say you go up to 30, right? Maybe after which things may not go well. So that's why you start with the steps by when you actually change the material, or when you actually go for a multi-material. So that is the way, I mean, typical that we follow. But again, otherwise it is not easy when you actually mix two different materials. Yeah. Any other questions? Okay, so I think we are now 3:30. We'll go for